Hello and welcome to the concluding lecture of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to derive Shockley equation, which gives the relationship between current and voltage in a p-n junction. So last time, we found an expression for the total current by evaluating the current of electrons at the interface between the depletion region and the p-doped region, in other words, at the minus xp point, and the current of holes at the interface between the depletion region and the n-doped region, in other words, at the point xn. And we found this expression in terms of the excess concentration of electrons at the minus xp point and the excess concentration of holes at the xn point. But since our final goal is to find an expression for the current in terms of the external voltage, we need to obtain these two concentrations in terms of the external voltage. So that is our job this time. Now, since our job is to find these concentrations in terms of the external voltage, we need to remind ourselves of how the external voltage appears in the band diagram. So this is a plot of the band diagram as we have already examined, and recall that the external voltage is the difference between the quasi-Fermi levels. So the region where the band is bent is the depletion region, so the point minus xp would be this point here, and the point xn would be this point here. And notice that I drew the depletion region exaggerated here just to make it easier to see. Now, we want these two concentrations in terms of the external voltage. And since the external voltage depends on the quasi-Fermi levels, then we need these concentrations in terms of the quasi-Fermi levels. So we need these two equations that we discussed in lecture 30. They connect the concentration of free electrons. Mind you, this is the total concentration. It's the sum of the concentration in equilibrium plus the excess concentration. So this is the total concentration of free electrons, and it is given in terms of the quasi-Fermi level of electrons and the Fermi level of an intrinsic semiconductor, which is a reference level at the middle of the band gap, and I'm not drawing it here just to avoid clutter. And this is the concentration of holes against, again, the total concentration in terms of the quasi-Fermi level of holes and the intrinsic Fermi level. So let's begin by evaluating the concentration of free electrons at this point minus xp. So here we have the expression. It's just this concentration evaluated at the point minus xp. Since the only parameters that depend on space are the Fermi level of the intrinsic semiconductor and the quasi-Fermi level, I am showing them here as a function of space evaluated at the point minus xp. And we also have the expression for the concentration of holes at the same point minus xp. Again, the quasi-Fermi level of holes and the Fermi level of the intrinsic semiconductor evaluated at the point minus xp. So all these energy levels, they are evaluated at the interface between the p-doped region and the depletion region. So at this point here, where the band stops bending. Now we can take their product, and since we are this Fermi level of an intrinsic semiconductor is evaluated at the same point, this is the same Fermi level. So since it's negative here and positive here, they will cancel out when we add the arguments of the exponentials. So we will end up with this product as being the product Ni pi times the exponential of the quasi-Fermi level of electrons. Notice that it is positive because we have negative and negative, and the quasi-Fermi level of holes, which is negative because we have this negative sign. And this difference, so this difference, this level minus this, is the external voltage times the magnitude of the electron's charge. So we have an expression for the product NNP in terms of the external voltage. So that's already a good progress. But we can simplify this expression further if we recall that in equilibrium, the quasi-Fermi level of electrons and the quasi-Fermi level of holes, they become equal, and we call it a Fermi level. So in this situation, this expression here with the Fermi level here and this expression here with the Fermi level here, they become almost identical, but one is the negative of the other. So we have the intrinsic Fermi level minus the Fermi level here and the Fermi level minus the intrinsic Fermi level here. So when we take the product N naught P naught, in other words, this term and this term with the Fermi level here and here, and recall that we are using the subindex 0 to denote the situation in equilibrium. So when you take this product, we end up with the same value we get for an intrinsic semiconductor. So that means that in equilibrium, the product of free electrons and holes, it's fixed, it doesn't change. Doping doesn't change this product. And this is a conclusion that we had already reached in lecture 24. So we can use this equality here to replace this product with the product NNP in equilibrium. So doing that, we have that this product will be equal to the product NNP. It doesn't matter where we take this product since we are at the situation in equilibrium, but it makes sense to take the product at the same point minus XP. And that makes sense because since this term here, this term, is the concentration of holes in the p-doped region, so it's at the interface between the p-doped region and the depletion region, so it is the concentration in the p-doped region. And this term is the concentration in the p-doped region when the system is in equilibrium. And since these two concentrations, they are almost identical, because as we discussed in lecture 31, when the system is taken out of equilibrium, the concentration of holes in the p-doped region does not change significantly because this concentration is very high. And the same happens also in the n-doped region for electrons. In other words, the concentration of majority carriers, holes in the p-doped region and electrons in the n-doped region, is not significantly changed when we take the system out of equilibrium. So that means that the concentration out of equilibrium is almost identical to the concentration in equilibrium, like we discussed in lecture 31. So that means that we can cancel these two terms out. And we end up with an expression for the concentration of electrons at the interface. Recall that this is a concentration of minority carriers, so it is different from the concentration in equilibrium, and we've just found that the difference is given precisely by the external voltage. So we're going to store this equation here and follow the same reasoning now for the concentration of electrons and holes in the xn point. Now we are talking about concentration of electrons in the n-doped region. So electrons are now the majority carriers, which means that the concentration of electrons out of equilibrium is almost identical to the concentration in equilibrium, which allows us to cancel these two terms and end up with the concentration of holes, which now are the minority carriers. And you can see that the concentration of holes out of equilibrium is equal to the concentration of holes in equilibrium times the exponential term. In other words, this concentration is modified by the external voltage. Now we also store this equation here, clean the screen, and we now focus attention on obtaining the concentrations of excess charge carriers. So beginning with free electrons, we know that the total concentration is the sum of the concentration in equilibrium and the excess concentration. So here we have this expression evaluated at the point minus xp. And we have just found that this concentration is given by the concentration in equilibrium times the exponential. So all we need to do is to solve this equation for the concentration of excess electrons. We just move this term over here and group the terms multiplying and not. So we end up with this very important expression for the concentration of excess free electrons. And notice that when the system is in equilibrium, in other words, when this voltage here is 0, then this concentration is 0 as expected, because we're going to have 1 minus 1, which is 0. And we can do the same analysis for the concentration of holes at the interface between the depletion region and the n-doped region. We've just found that this concentration is given by these expressions. Then we solve for the excess concentration and get this expression. So we have now concluded our main job, which was to find the excess concentrations in terms of the external voltage. So all we need to do is to replace these two expressions over here to obtain the current in terms of the external voltage. And we can group the terms multiplying these brackets to rearrange the expression in this more organized form. And also recall that we are ultimately interested in the total current, and the total current is the current density times the cross-sectional area. So to get the total current, all we need to do is to multiply by the cross-sectional area, like we've done here. And this term, which multiplies this bracket, we group it into a single term, which we call the saturation current. So it is this I naught term here. It has units of current. It is called the saturation current. So when we use this definition of the saturation current, we finally obtain what is called the ideal Shockley equation. Now let's examine the ideal Shockley equation in more detail. So recall that we have assumed forward bias configuration to deduce the ideal Shockley equation, but there was nothing in our derivation that was specific to forward bias condition. And that means that the ideal Shockley equation is valid for both forward and reverse bias. The only difference is the sign of the external voltage. So recall that the external voltage is given by this expression. So it is the difference between the quasi-Fermi level of electrons and the quasi-Fermi level of holes. And when we are in forward bias, the quasi-Fermi level of electrons is higher than the quasi-Fermi level of holes, which means that this is a positive number, which means that the external voltage is positive. But when we are in reverse bias, the quasi-Fermi level of electrons is lower than the quasi-Fermi level of holes, which means that this is a negative number, which means that the external voltage is a negative number. So when we are in reverse bias, we have negative number here. The external voltage is negative. When we are in forward bias, the external voltage is positive. And notice that in reverse bias, we're going to have the exponential of a negative number, which will be much smaller than 1, which means that the total current is approximately equal to the saturation current. And in forward bias, then we're going to have the exponential of a positive number, which will be much larger than 1, and the total current now depends exponentially on the external voltage. Now notice that the saturation current depends on the concentrations of minority carriers. This is the concentration of free electrons in a p-doped semiconductor in equilibrium. And this is the concentration of holes in an n-doped semiconductor in equilibrium. And we have already seen that these concentrations are very low. The concentration of free electrons in a p-doped semiconductor is very low. The concentration of holes in an n-doped semiconductor is also very low. And that means that the saturation current will be typically very, very low. To give you an example, in silicon diodes, this current is of the order of nanoamperes. So that means that in reverse bias, the current is very, very low, which means that the p-n junction operates basically as an open circuit. So here we have a plot of the ideal Shockley equation, assuming the saturation current of 1 nanoampere. And as you can see here in the blow curve, when the voltage is negative, the current is so low that we cannot even see it in the plot. So that means that in reverse bias, negative voltage, the junction is behaving as an open circuit. But when the voltage is above 0.4, then the current increases exponentially with the voltage. And that means that there is a huge range of currents that are accessed by a small variation of voltage around 0.55 in this example. So we say that the operational voltage of the diode in this example is around 0.55 volts, and the diode is behaving essentially as a short circuit, having a small voltage drop in it around 0.55. And in the textbook, you can find further discussions about the behavior of a forward bias p-n junction as a short circuit. But for now, I want to call attention to the fact that the ideal Shockley equation was derived assuming ideal conditions. But if we had taken into account some non-ideal effects, like for example, recombination in the depletion region, then we would get Shockley equation, which is almost identical to the ideal Shockley equation, but with the addition of this parameter, which is called the ideality factor. So when the ideality factor is 1, we get the ideal Shockley equation, like in the blue plot here, where we have an ideality factor of 1. And I'm showing at the black plot the effect of an ideality factor different than 1, in this case 1.3. And as you can see, the main effect is to change the operational voltage of the p-n junction, which in this case now is around 0.7. And in the textbook, you can find examples of applications of p-n junction and some discussions about how to analyze circuits involving p-n junctions. And with that, we conclude our lecture series, which covered chapters 1 to 3 of the textbook. I hope you have enjoyed it, and I hope to see you in a future lecture series. Goodbye.